So arc length. I'm going to look at our arc length curve. So when your equation is from Michael's, you can get one.
All right, so our formula for if your function is in the form y equals or f of x equals, then your arc length is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. Similarly, if your function is in the form x equals or f of y equals, then your arc length is equal to the integral from c to d of square root 1 plus f prime of y squared dy.
So if I look at example 1, given y squared equals x cubed, we must find the arc length from 1, 1 to 4, 8. So if I solve this for y, I will use the root of both sides. And get y equals the square root of x. Which is 3, right? And y equals the 3. Which gives me, if I derive that, 3 times x to the 1/2, which can also then be written as 3 halves times the square root of x. So my f prime of x is 3 halves times the square root of x. And because I'm dealing in terms of x, I only care about my x values at my points. So I'm going to take the integral from 1 to 4 of the square root of 1 plus f prime of x, which was 3 times square root of x squared dx. If I then simplify that as much as possible, so I simplify my square. 3 squared is 9, 2 squared is 4, square root of x squared is just x. Dx. And because this is a definite integral, we can solve this using our graphing calculators. So we are going to graph the function, the square root of 1 plus 9/4. Option 7, figure a area of your curve. So that tells me that my arc length of that curve from 1 to 4 is approximately 7.634 units. If I look at example 2, I'm doing y squared equals x from 0, 0 to 1 to 1. And this is a function where it's already solved for x, it's already at x equals, so we're going to use our secondary formula for arc length for our equation of x equals. And so we're going to find f prime of y. If I differentiate y squared, that becomes 2y, or 2y to the first, okay. And because I'm dealing in terms of y, I care about my y values. So I'm going to integrate from 0 to 1, square root 1 plus f prime of y, which is 2y squared, dy. And we continue to simplify them. We have the integral from 0 to 1 plus 2 squared is 4, y squared is y squared, 1 plus 4y squared. And again, because this is a definite integral where we're going from 0 to 1, we are going to graph the square root of 1 plus 4y squared, and our graphing function there are 1 plus 4x squared. And the integral of that. Okay, so if I graph 1 plus 4y squared, square root of 1 plus 4y squared, do the second calc to find the integral from 0 to 1, what do I get from that?
1.8.
So in example 3, I'm given a function x, y equals 1 of all the functions. And we're asked to find the arc length from 1, 1 to 2, 1, 10. And so in this case, we can solve this function for either x or y. I think that it's easier to have functions in the terms of y equals x. That's the function we typically deal with. So we're going to solve this for y. Divide both sides by x. So y equals 1 over x, which can also be rewritten as x. Then from the other if I'm derivative of that, that's from of x. If I derive that, we get negative 1x, then negative 2, which I can rewrite as negative 1 over x squared. And because I'm dealing in terms of x's, those are the values I care about. And the first way, we take the integral from 1 to 2 of the square root 1 plus negative 1 over x squared squared dx. And we can simplify that. Well, negative 1 squared is 1, x squared squared is x to the 4th. So I get the square root of 1 plus 1 over x to the 4th dx. And this is a definite integral with integral limits from 1 to 2. So we're going to graph the square root of 1 plus 1 over x to the 4th in our graphing calculator and use our integrate function to find the arc length. Okay, so Mark, what do we get for the arc length?
1.132.
1.132. 1.132. Okay, so that is what we are working on today. We're going to do 5, 6, 7, 7 through 8.